So in this video we're going to look at the convergence of series or infinite series. And before we go into anything, just a little review. A series converges means that the sum is finite. The series diverges means that either the sum is infinite, sum of infinity, positive or negative, or this limiting process that we would use to get the sum does not exist. Second thing to go into this already knowing, if we have a geometric series, we already know that this converges if the common ratio is between -1 and 1 and diverges otherwise. So this is just some precursor knowledge needed for this. So let's dive right in. Limit of terms. In order for a series to converge, the terms need to approach 0. So I know this. If the limit as n approaches infinity of the terms of the series, or the terms of the sequence added up, is not 0, then the series, which is that sum from some number, I'm going to start at 1, but it could be any other positive number, or 0 depending, the sum of the terms diverges. And that should make some sense. That if I'm adding up infinitely many things, the only way for this to settle down is if, as I get very far down the road, I'm adding on things very close to 0. An example? Does this converge or diverge? And here's the way to deal with this type of problem. I have this sigma notation, which means I'm putting in 1, then 2, then 3, then 4, all the way up to infinity. And it'll be helpful to actually see what this series or sequence looks like. So I put in 1, I get the cosine of pi over 2, which is 0. When I put in 2, I get the cosine of 2 pi over 2, which is the cosine of pi, which is -1. When I put in 3, I get the cosine of 3 pi over 2, which is 0. When I put in 4, I get the cosine of 4 pi over 2, which is 2 pi. Cosine of 2 pi is 1. And then it actually cycles through. When I put in 5, I get 5 pi over 2 in here. Cosine of 5 pi over 2 is 0. I get -1. I get 0. I get 1. And it continues in this pattern, repeating every 4 elements. And if I look at this, I see that the terms, so the limit of these terms as n approaches infinity is not 0. It's not approaching anything. It's going to keep on alternating from 0 to -1 to 0 to 1 to 0 to -1 to 0 to 1. It never settles down to 0. So because of that, the series diverges. Now, to help explain why it diverges, you can look at the partial sums. S1 is 0. S2, the sum of the first 2, is -1. S3, the sum of the first 3, is -1. And S4, the sum of the first 4, is 0. And then it just keeps on going. 0, -1, -1, 0, 0, -1, -1, 0. Never settles down to a single value, so it diverges. Next, direct comparison test. So what we have here is, if I have a series, so if I have a series, so the sum of some things, here I'm going to sort of have an infinite series, converges, and I know at least for some point on that I have another sequence that is bounded by this sequence, then the series T also converges. And that should make sense. The fact that this converges means that its sum is finite. If these terms are always smaller than those terms, then this sum also needs to be finite. Now, I guess I should put in here, I'm considering u sub n and t sub n all non-negative. Okay, if we have negatives, things are a little bit different. But in this case, if this converges and t's are all less than u's, then t converges. And similarly, if the sum of u's diverges and the t's are bigger, so this goes off to some type of infinity, and the t's are even bigger, or it goes to something that's not, it's DNE, then the sum of the t's, of course, has to diverge as well, because it'll be sort of even worse than the u. And let's see an example of that in this. So I have 1/2 plus 1/3 plus 1/5 plus 1/9 plus 1/17. And like, okay, what's the pattern? What's the pattern? Well, I see I have 2 plus 1 is 3, plus 2 is 5, plus 4 is 9, plus 8 is 17. So I guess the next one's going to be plus 16 down here, which gives me 33. But we're still sort of missing the point. And here's the idea. The fact that I'm changing by 1, 3, sorry. The fact that I'm changing by 1, 2, 4, 8, 16, 32 should lend us to say, okay, I know what's happening here. This is a following a 2 to the n rule, so 1 over 2 to the n. And I can see that this sum from n going from 0 to infinity is going to be 1 plus 1/2, then put in the 2, plus 1/4, plus, put in the 3, 1/8, plus, and we can see, all right, this seems to line up nicely. The first term here and the first term here, this one's bigger. The second term here and the second term here, 1/2 is bigger than 1/3. The third term and the third term, 1/4 is bigger than 1/5. And you can sort of see it now. The fourth term and the fourth term, 1/8 is bigger than 1/9. This is geometric with common ratio equal to 1/2. We know this converges. So we have geometric common ratio equal to 1/2. So that converges. We know that the terms are less than or equal to these terms for all n. And therefore, this series also converges. So the direct comparison test is super useful, super powerful, but it can be hard sometimes to see what that U series or U sequence is. This one is actually very useful, easier to get started, but can be difficult to finish off. And here's the idea. The limit test basically does this check. It checks to see if the terms approach 0 fast enough. And how it does it is the following. We're going to take the limit as n approaches infinity, so I go off towards the end of my sequence, of the ratio of two consecutive terms, the n plus first term and the nth term. So this would be like the 11th term divided by the 10th term, or the 101st term divided by the 100th term, or the 997th term divided by the 996th term. And I'll say that's L. And there are three cases. If L is between -1 and 1, the series converges. It means that the terms are going towards 0 quickly enough. If L is outside of -1 and 1, so L is either less than -1 or L is bigger than 1, the series diverges, because the terms are actually getting bigger, they're getting further away from 0. And the final case, if the limit equals 0, then the limit test is inconclusive. So in this case, you're going to have to do something different, whether that is finding a direct comparison or seeing if you have a geometric series or something else. This, if you get L equals 0, I can't use the limit test to figure it out. Let's look at two examples for this. Here's one. So this whole mess right here is my general term. So I'm going to start by taking the limit as n approaches infinity of, I'll have this in the denominator, so n2 to the n over n factorial. And I will have the next term in the numerator, which basically everywhere I saw an n, I'm going to have an n plus 1. So I have n plus 1, 2 to the n plus 1, divided by n plus 1 factorial. And there are a few ways to deal with this. I think the easiest way to deal with this is you can either flip this, multiply by the reciprocal and bring it up here, or you can consider where things go. So I think it's nice to look at this. Think of the exponents like multiplying positives and negatives. This is in the numerator of the numerator. It's like two positives. So the n plus 1 and the 2 to the n plus 1 remain in the numerator. This is in the denominator of the numerator, so that's like a negative times a positive. It's going to end up in the denominator. I'm going to put it here at the end because this one's going to sort of pair off with that one. So I have an n plus 1 factorial. This is in the numerator of the denominator, so it's like a positive times a negative. It will still end up in the denominator, so I have n down here, 2 to the n. And this is in the denominator of the denominator. It's like a negative times a negative exponent comes up to the numerator. All right, dealing with these things. So in here, we still have the limit as n approaches infinity. N plus 1 over n, as n's getting closer to infinity, goes to 1. So I'm just going to sort of cross it off. It's sort of n behavior. I have the biggest term here is n, biggest term here is n, so those go to 1. I have one extra 2 in the numerator. I have 2 to the n plus 1 divided by 2 to the n, so there will be 1, 2 left over in the numerator. I have one extra term here, so a little sort of rationale here. If this n is 7, this down here is 8 factorial. I know that the numerator is 7 times 6 times 5 times all the way down to 1. The denominator is 8 times 7 times 6 all the way down to 1. And you can see there's one extra term down here. There's one extra term down here. That's n plus 1. As n approaches infinity, this approaches 0. And because of that, then this converges because of the limit test. This is between -1 and 1. So that's really great. It's easy to start off doing. Just sort of set up the fraction, work out the fraction, reduce things down, and address the answer. This one's a little bit tricky though. So I'll do the same thing and we'll see what happens. So in here, I'll start off with the limit as n approaches infinity. In the denominator, I'll put the nth term, 1 over n squared. In the numerator, I'll put the n plus first term, so that's not how you write n plus 1 squared. You can see I just replaced the n with an n plus 1. And same process, so limit as n approaches infinity. Numerator of numerator stays up top. Denominator of numerator, it's in the bottom. Stays in the bottom, goes to the top. And this here is the same thing as the limit as n approaches infinity of n divided by n plus 1 all squared. Just like before, this approaches 1. And so what that means is the limit test is inconclusive. I'll need to do something different to figure this out. So what can I do? Well, just like with improper integrals, I know that this converges if p is greater than 1 and diverges otherwise. The reason behind that is, just like with improper integrals, when p is greater than 1, you can take an antiderivative that will approach 0 as we go off to infinity, and I can evaluate it. If p equaled 1, I would get an antiderivative that is natural log, and natural log is undefined as we approach. It goes off to infinity as we approach infinity. If p is less than 1, if p is less than 1, then when I take the antiderivative, I'll end up having an x in the numerator. So if I have a sum or a series like this, as long as the power in the denominator is greater than 1, it's going to converge. So looking back at this same example, I see that I have 1 over n squared. This one converges, and it's much simpler. Converges since p is greater than 1. So in this case, doing the limit test didn't solve it, but it's actually a really easy problem if you notice this. Okay, so what about the harmonic series? And the harmonic series, for those that don't know, is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... So this is the sum as n goes from 1 to infinity of 1 over n. And based on the rule we just saw, p equals 1, so the harmonic series diverges right off the bat. You can actually put it into a calculator and do partial sums and see that it goes off towards infinity. It goes off there somewhat slowly, but it does go off to infinity. Okay. Final rule, alternating convergence. So this is really nice, and if 3 things are satisfied, the limit as the n goes to infinity of the terms is 0, so it's approaching 0, and the magnitude of the terms, so the magnitude of the next term, is less than or equal to the magnitude of the current term, so it's somehow decreasing, at least at some point. It doesn't need to be all the way through, but at some point it starts that these terms are decreasing, and it's alternating. That means I go from positive to negative to positive to negative. Then the series converges by alternating convergence. On a side note, okay, so this one converged basically because I'm adding and subtracting. I'll go into a little bit more in a second. But on a side note, if the series of the magnitudes of t, so all the positive, changing all the negatives to positive, converges, it is said to converge absolutely. So this is even stronger. Some things will converge absolutely, and some things may only converge if we allow for the positives and negatives. Before I go into an example, why? Okay, so why does this happen? Well, let's talk about that. So here's the idea. I'll start off with a positive. So I'm going to be at some value and take a positive step. I get to a new point. So that's Tn. Let's say that's T1, that's T2. And since I'm alternating, the next step I'm going to take is backwards. But since my terms are decreasing, I cannot go backwards further than my starting point. So I can get to my starting point if they happen to be equal, but I can't go further. And then, since I took a step backwards and it's alternating, I have to take a step forwards. But it has to be at most the same size step, so I can't go past this point. And what happens is, since my terms are decreasing and alternating, I'm sort of stuck in a smaller and smaller range, and the last saving grace is eventually my step size is 0. It is actually getting smaller and smaller. Like, I can go back here, I can have the same step size, but then eventually it's going to get smaller and smaller and smaller and get to a limit. So let's look at this. This looks a lot like a harmonic series, but this is actually alternating harmonic. And we notice the three things. So first off, the limit as n approaches infinity of, I guess the terms are -1 to the n minus 1 over n does go to 0. You see, you're dividing by larger and larger numbers. Check. Second, the terms, so the following term has a magnitude less than or equal to the previous term. You see, 1/2 is less than 1. 1/3 is less than 1/2. 1/4 is less than 1/3. Notice I'm not taking into consideration the negative, I'm looking at just the magnitude. So check. And it is alternating. Changing signs, positive, negative, positive, negative. This numerator here, a -1 to an exponent, causes that. And because of that, it converges. Now, it is worth noting, this only converges because it's alternating. This does not converge absolutely, because we just talked about the harmonic series not converging. I hope that helped out. I know it was a relatively long video. I'll try to get these shorter again, but there's a lot of stuff I want to cover in these things. Feel free to comment below with questions, and I'll get back to some more of this later on.